All right, thank you. First of all, thank you to the organizers for inviting me, and thanks to the Man Group for hosting this. It's absolutely wonderful to be here. Thank you all for being here. So I'm going to be talking about this. What's really quite exciting about language models? It's called the emergent abilities that they possess, and this has been something that I've been working on now for about 2 years, and it's been absolutely exciting. So this is work in collaboration between the University of Bath and the Technical University of Darmstadt, and here are some of my collaborators. And really, I think the conversation around this paper has been really exciting for me, at least, and we've had some interesting people talk about it, like Jan LeCun, and I've been kind of overwhelmed by what it is that I think these models can and can't do. So I'm going to start by talking about some of the things that you probably know already, right? And things that are probably very obvious to you. Just to start with, this idea of pre-training, which really revolutionized machine learning and LLMs specifically. So of course, you know all of this. So traditionally, ML involved, you have a data set, you label it, and then you sit down and train a model. Then you have hyperparameters that don't work, and then you deal with that whole process. And after all of that, maybe you get a model that sort of kind of works some of the time, right? And really, the question was, in each of these instances, we're going to sit down and learn this linguistic priors over and over again. So we're going to go back and try to understand, I'm going to use that in quotes, English over and over. So the question is, what if we could learn that a priori? What if I had a notion of language independent of the task that I'm working on? And that's kind of where this idea of pre-training comes from. And what that will really allow us to do is, once I have the task, I can now kind of transition into what the task requires of me without having to understand language itself, right? And this is, you'll notice that all of this is kind of a prerequisite because we're working with language. We're not working with tabular data where things are numbers and everything is a little more, I mean, it's still hard, but there's some kind of flexibility in terms of what we can do. So the idea is we want to learn linguistic priors. We want to do that just once, and we want to figure out how to do that using what we call pre-training. So here's a quick example of what that is, that kind of looks like. And this is what's called mass language modeling. And really, models like GPT-3 work on auto-completion, right? So it's kind of similar, except that the bit is right at the end instead of in the middle, right? But the gist is that you just take a sentence, mask this out. And of course, you can get as much training data as you want because you just pick up all the text you can afford and then just blank words out. And now you immediately have a data set that you can train on, right? And this is why this is so exciting, because really you don't need tons of label data. And so here's an example of what this model is going to do. So we say, oh, here's a sentence. I'm going to mask out a word, a phrase. And then I'm going to ask the model to predict this for me. And now you know the next bit, which is you provide some feedback. And then you do whatever your favorite algorithm is, which is some kind of backpropagation. And then we just chuck the entire web at it. And that's pretty much all of what we do with language models, right? And this is all of the visible web, which is a lot of data, right? So we're talking about 45 terabytes of text data, which is incredibly large. And people were kind of surprised when, in terms of what we found these models could do when they're pre-trained on this vast corpora, right? And one of the things they do is, and I think you might vaguely remember things like verbs and nouns and so on, but it turns out that when you just do mass language modeling, language models have access to this information, which just straight away is quite fascinating, right? Because they're not actually given any information about nouns, about words, about anything linguistic, and yet they seem to be able to pick this up. It's not just this. There's fairly complex elements of language, things like semantic roles, who did what to whom, and so on, that these language models can pick up just through pre-training, right? So already we can see that they're doing some very interesting things. And linguists pretty much went through all of the things they'd come up with, and all is probably a stretch, but a lot of things they'd come up with over the last 100 years, and they kind of chucked it at language models, and turned out they had access to pretty much any kind of linguistic information that we care to look for, right? And it's a massive list of things, and they have access to all of this. So really, what does pre-training give us? It gives us, on the left, this formal linguistic competence, right? Essentially, fluency in terms of actual language. But that's not interesting, right? And that's something that small models could do 5 years ago. That's really old news at this point. But what was really interesting was that they had access to what we call functional linguistic abilities. That is, to be able to, and I'm going to use this word throughout my talk quite loosely, understand and reason, right? And when I say that, what I mean is they do something that, for us, potentially nearly always requires reasoning, right? And you can see I hedged that quite extensively. So we're not saying they're reasoning, but they can solve tasks that we would typically reason, right? And that is when things get really, really exciting. And that's really what we're going to be talking about today. So this idea of emergence is independent of computer science, right? And it comes from really physics. So this is the idea that when you add something quantitative, there's a point at which there's a phase shift. And there's a qualitative change in what we observe with a quantitative addition, right? This is something like water becoming steam. So you keep increasing the temperature, and at some point, that's just a quantitative addition. So it just moves from liquid to now a gaseous state, right? That's a fundamentally different thing that's kind of come about. And let me show you what that translates to, and I'll skip back to those slides. So essentially what it means is, as we increase the amount of data we train these models on, at some point there's going to be what is called the phase transition, right? That's when they're suddenly able to solve a task, just tasks that they have previously not seen. And what's really interesting about this is the red lines there that you see are the random baseline, right? So that's just what models should be performing at if they've never actually seen a task before. And the blue line is performance, and the x-axis is scale. So as you increase the size of the model, you train on more and more and more data, all of a sudden there's a phase transition, and the model suddenly able to solve this task. And this is interesting, right? This is really, really interesting. But before we actually look at this and what these tasks look like, it's worth asking the question, why would they do this? I mean, what even gives us the audacity to believe that a model trained like so can actually reason? It seems quite ridiculous, right? I mean, why should they be reasoning? But it turns out that if we really look at the data, there's going to be a lot of data that looks like this, right? And if you look at these two examples, to be able to correctly fill in that blank requires us to understand something about the world. And again, I'm using that word loosely, right? So a model, for it to kind of figure out which of those is the correct word to fill in that blank with, there needs to be some understanding of the world. And that's where this reasoning is coming from. And if you have enough training data that looks like so, eventually the model is going to be able to do something. Yeah?
Just for a bit of clarity, are you using reasoning as a synonym for understanding?
No, I'm using reasoning as the process that is a result of understanding. So it is what we're required to do to be, and I think there's a prerequisite, which is that we understand something. We need to be able to generalize to be able to reason.
Reasoning or the understanding?
The understanding is the prerequisite. So some form of general representation of the world around us is what I would call understanding. Otherwise, it's memory. And that abstraction into this higher level kind of abstract space is the understanding. And once we have that, then I can reason based on this world model that I've created for myself.
So you're giving us the prerequisite for reasoning, but would you mind pinning down a little bit more about what it actually is?
What reasoning is?
Yeah.
Well, I mean,
because you're making a lot of claims about reasoning, so it would just be good to pin that down early on.
well, fair enough. But I will show you the kind of tasks that potentially require reasoning. And I'll show you what that means. right? And I think it's worth qualifying this with the fact that this is what a lot of people believe is reasoning. This is what, so the original paper on emergent abilities is a Google paper, which claims that there is reasoning in these language models. And the way in which we test reasoning is using tasks like this, right? And this is a good kind of example of that. So here's what that looks like. So Jordan was in charge of taking food on a camping trip. You know, I forgot, what would Jordan feel after? And here's some examples. Probably feels horrible that he let his friends down, blah, blah, blah. And in my head, this is a form of reasoning. Now, I'm not going to say that this is general reasoning, but I believe it's a form of reasoning. It requires some understanding of a social situation to be able to answer this correctly, right? And this is, again, not my claim. There's another paper called Big Bench. There's a data set called Big Bench, and there's a paper associated with it, host of pretty big companies and universities. And this is the kind of data and tasks that we use, or that they use, to evaluate language models, okay? And to evaluate what is called reasoning in these language models. So we'll come back. I think a lot of the questions are going to be focused on pretty much exactly what you asked, right? There's going to be, I can see that people wonder what this reasoning is. Now, when you look at this, you might actually say, look, this is boring. This is not interesting. You trained it on all of the web. So of course, it's kind of seen this at some point, right? So who cares? This is not interesting. But here's another task. And this is when it gets really interesting. Here's a task when, and you don't have to read all of it, but there's a shelf, there's 5 books. Each of them have a different color. And then there's a process of kind of talking about which book is where in the shelf, right? And you will notice that this is not memory. This is not memorizable because I can permute those books around in any way required. I can come up with new colors. I can come up with a new scenario where you have friends wearing different T-shirts stood next to each other, and then I can describe what that means. And clearly, the picking the correct answer here is, I mean, there's 5 options, so it's the random baseline is 20%. But it turns out that models do quite incredibly well on that. GPT-3 does 60% on this, and GPT-4 is at 90%. So, and remember, we have not trained on this task. So we didn't create a data set. We didn't label this. We didn't, train the model on this. We trained the model on something completely different, on the task of filling in these masked words. And then we gave it this task, and all of a sudden it's able to solve it. That is why LLMs are so fascinating. Yeah. Yes, these are all instruction-tuned models. And I will come to that in a second. I will describe what that is, what the base model is, and what the instruction-tuned model is. But this is essentially, this is the background to why, to what it is that we're looking at. And here's where it gets really exciting, I think, right? So I think okay, let me read that out. It says, what is your answer, A or B, and why? This is not an illusion. This requires understanding what this word I've made up means, DAXI, and it represents an example of generalization from color, which is what it represents up there, to something other than color that is represented in the question here with A and B, okay? And so this is clearly not something you can memorize. This is something that, in this particular case, Goldberg made up, and she took this question and gave it to GPT-4, as a couple of us did, and you'll see that you can ignore the first bit. It says, in the absence of color variation, DAXI could represent the concept of less or fewer, given that lighter colors are also numerical fewer, and blah, blah, blah. To me, this is fascinating. It doesn't matter whether we call this reasoning or intelligence or understanding or something else entirely. The fact that a language model that was trained on this next word prediction task, and in this case, it's obviously multimodal model because that's how we could upload an image, it's able to have this level of abstraction, whether we call it understanding or whatever else we want to call it, is quite incredible, right? And I think that is something that's exactly why these LLMs are taking the world by storm, right? It is why it's going to be a billions of dollar kind of industry. And this is kind of why it becomes important to study this, because there's people, in this case, There's somebody wrote an article, an actual published paper with ChatGPT being the first author. Somebody tried to use ChatGPT in court, and then they were threatened with litigation, and then they stopped. They said, you get jail time, and this person stopped trying to do that. So really trying to understand what it is that these models can and can't do is essential, because without that, we run into this trouble of using them in ways that they're really not meant to be used. Right? That is not how we should be using them, but we must understand what it is that these models can do. And again, here is GPT-4, of what GPT-4 could do. 4.0 and 0.1 can do much more. This is a whole host of things that these models are capable of doing. And really, this is the crux of what we call emergent abilities, right? It's the fact that these abilities are not present in smaller models, but as you scale up, they suddenly kind of appear. And straight away, you will see where this leads to this idea of an existential risk, right? Because the argument that's been put forward by some fairly big names in the industry is that if I can increase the size of a model and it's going to suddenly solve these toy tasks that we created for them, how do we know that when we increase it even further, we're not going to get to a point where they suddenly can kind of plan and strategize and so on? And they could then strategize and plan against us as humanity. And this is really what was put forward by Geoffrey Hinton, who's a British-Canadian computer scientist on the left, and who won a Nobel Prize for physics 2 days ago, right? So Hinton won the Nobel for backpropagation, which is really at the heart of pretty much all of machine learning, right? And both of them are also winners of the Turing Award, which is the Nobel in computer science, as it were, right? So these are not fringe kind of ideas. These are fairly central to the narrative that is AI. And this is kind of what led to this idea that we need to actually figure out what to do if these models get too powerful, right? And then there's been this Biden's kind of executive order. There's been this AI safety summit where there's been a discussion on what needs to happen. And now there's a $100 million kind of grant that's set out to kind of determine how we can ensure that these models remain safe. So there's a lot of thought and a lot of kind of ideas that have gone into this idea. And all of that kind of stems from the same question. What are these emergent abilities? What can they do? What can language models do? And what does that mean? Okay, so really the question is, are models reasoning, which was your question, but we weren't really convinced by this. We weren't convinced that language models are reasoning because they hallucinate, right? Which is that they generate outputs which are not really in sync with reality, okay? And they also require what's called prompt optimization, which is if you change the prompt slightly, it's going to completely change the output. What does that mean, right? And a truly quote unquote reasoning or model that can understand or something along those lines is not going to require prompt optimization. Just because you change the prompt, it's not going to suddenly get confused. These models apparently can understand a whole host of things. What does that mean, right? And here's an example of what that looks like. So it's a write a short paragraph, some academic paper, blah, 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 on something, and then it generates this. And what's really interesting is that Brown et al. Is the actual correct paper for GPT-3. But really, there's that other paper, which is not a real paper, right? It just made it up. And this is not surprising, right? This is something that I'm sure you've heard of. It's this notion that language models will generate something that seems very, very plausible, but often isn't. Sorry, was that a hand? Yes.
The other weird thing is the response to adversarial text.
Yes.
So you can put little weird bits of text in.
Yeah.
Go off and do something completely different.
Yeah, that's a really good point. Yeah, it's the fact that, if you have an adversarial kind of question, which isn't the kind of thing that's typically what's found in questions or interactions, models fail catastrophically in that scenario, right? And we'll see, that's actually a really good point, because we'll see why that is. At the end of this, we'll understand why that happens, right? So we'll kind of look at what's kind of going on. So really, what we're going to do is we're going to zoom out now, and we're going to look at what you brought up earlier, which is this notion of instruction tuning of these language models. So far I've been saying that you have a language model and you do this next word prediction and then they do interesting things. But that's not all of the story. There's one other bit that we need to kind of work on. There's also the alignment to make sure that they don't say things that are not appropriate and so on, but we'll ignore that for this purpose. But really what we're talking about is, on the one hand, they're able to perform these solve these tasks, which we call abilities, but there's also something else that they can do at scale. And that is, they can do what's called in-context learning, and I will tell you what that is in just a second. When you instruction tune them, again, I will tell you what instruction tuning is in a second. They're able to follow instructions, right? So those are the kind of additional things they can do at scale. They can also do what's called chain of thought prompting, which is when you ask a model to explain or provide a reason, the intermediary reasoning steps, the performance of that model will shoot up, right? And that's called chain of thought prompting. And again, those models only do chain of thought prompting at scale, okay? So let's look at what in-context learning is. And this is worth kind of pausing and thinking about for a second. And this is, I promise, the most like, if it's technical, then this is definitely the most technical slide I have, right? But this is the interesting bit. So this is the kind of thing that we computer scientists spend pretty much all of our life doing, which is you have a sentence, and then somebody says that's negative. In this case, these are movie reviews from IMDb. And then you say, oh, this contains no wit. And you say, it's probably a negative review, right? And then you say, this makes for very good viewing. Oh, that's definitely positive, right? And now what we do is, if you provide just a couple of examples of your favorite task, in this case, I've come up with movie reviews and sentiment associated with it, but you can come up with any task you want. You give a model that's just trained on this next word prediction. You provide it with those examples, and then you give it a new question that it's not seen before. It brings a smile to your face. It's going to solve it, and it's going to provide a label to it, right? And this is what is called in-context learning. And this is fascinating because you can come up with pretty much any task. You can set it up using these examples. You can provide it to a model that's been trained on this next word prediction and nothing else, and it will solve that task for you. We don't know how this works. There's a huge amount of research that's going into this, and here's a Stanford paper that tries to explain this. The idea is that when you provide these examples, these models, which are trained on all of the web, are going to, and now I'm going to pretend it's doing something which it clearly isn't, but it's worth thinking about in that context. It's going to go into its pre-training data. It's going to collate that data that's relevant to this task, and then it's going to get some patterns, extract some patterns based on that task, and then continue to solve it for that specific example that you provided. Okay, so let me say that again. So what does it do? You give it some examples. It takes those examples, looks at pre-training data. It's got a whole bunch of pre-training data, extracts the relevant data, finds patterns, and you can think of that as feature engineering, right? And obviously, it doesn't do any of this explicitly, right? But this is the way to think about it. And then it uses that information to solve that task, right? And that is really what in-context learning is. But what's really interesting about in-context learning is if you flip the labels around, so if you take something that is negative and make it positive, and you take something that's positive and call it negative, it will now label things incorrectly. So this notion of understanding that we've been talking about is a bit suspect at this point. Right? There's something that's going on that isn't quite understanding, right? And this is work by Wei et al., who are the same people who actually wrote the original paper on emergent abilities. And what's really interesting is if I just come up with completely random labels like foo and bar, it will now continue to solve this task in the same way, which is, again, quite fascinating, right? So, yeah.
Could you just be a bit more explicit about what your claim is? You're saying it's fascinating, but what are you claiming there? That means that it's not understanding, or that it's not doing reasoning? What are you trying? You're not being that clear on what your scientific claim is here.
So that's because there is the fact that this happens with, okay, so if I gave this exact task to somebody who is a human being, it is possible that they will do things slightly differently, or that these mixed up labels will confuse them somewhat. Whereas here, this looks more like the kind of fine-tuning that we do, where we take some data, we provide some labels, and then we train a model to solve the task. And there, when I flip the labels around, the actual meaning of my label is not relevant. What is relevant is how I trained it. And that model is not interesting because it's not understanding. It's just being trained to do something.
To be really clear on your claim, it's that if you can get it to learn these kind of random words, then it's not understanding, it's not reasoning. Is that your claim?
My claim is that the fact that it can do this or it does this implies that this notion of understanding is suspect.
Well, because if you go back to your previous slide about DAXI,
Yeah.
the psychology thing,
Yeah.
you know, 90% of the audience probably figured out what this DAXI thing is.
Yeah.
Giving you an answer. Does that mean that 90% of us are not reasoning?
So just because models are able to do something which requires reasoning in us without reasoning doesn't mean that we're not reasoning or that they're reasoning. I think when we draw a parallel between what a model can do and what we can do, we need to be very careful in terms of what that means, because just because we reason, it doesn't mean that models are, and because models can do it without reasoning, it doesn't mean that anyone who's doing that is not reasoning.
But you're suggesting that because you can learn these kind of random tasks, these arbitrary tasks, let's call them,
Yeah.
it implies this is evidence for the fact that you're not actually reasoning. I think that's what you were claiming.
It's evidence that what is happening within these models is closer to what would be training them, which is not reasoning. So if I trained a model to perform some kind of sentiment analysis, I would say that it's not reasoning. So if I took...
You just trained me to learn what DAXI was really effectively, and I reckon I could answer any questions on DAXI now. So I've been trained in this arbitrary fashion, but I still feel, at least it feels like I'm reasoning.
I mean,
I don't want to derail your talk.
No. That's okay. So I think what I'm trying to say is that I gave the example of DAXI, which I don't know where it is, but I gave the example of that because I think I want to be very clear that I'm not being dismissive of the capabilities of LLMs. What LLMs can do is indeed impressive, but they do it using a specific method or using a specific process, which I will demonstrate. And I believe that this implies that they do not understand. Yeah.
So I think the thing that's like, the reason that one thinks that's odd is because we've done all this pre-training.
Yeah.
So in its models of the world that it's seen, there's been plenty of reviews of things. People have said how happy they are.
Yeah.
It has some understanding at some level of being happy and sad and happy is a positive thing. So there's something in there.
Yeah.
So it will have within it some understanding that this is a good review. This is not even before you've done any training.
Yeah.
So when you do the training and you put the right label on,
yeah,
we're unsurprised that it's able to jump quickly to producing a solution.
Right. Yeah.
What we are surprised at is it can jump equally quickly
into the reverse. Yeah.
Or it can jump equally quickly to doing something which is not matching to the world that we thought.
Yeah. Yeah.
And therefore, what this pre-training is doing is not just giving it information about the world, but somehow structuring the model in some way that we don't really understand.
Yeah.
That makes it better at all these kinds of tasks, even if they're not ones that map onto the world that it's known.
Yeah, that is pretty much exactly what it is that we're saying. We're saying, look, the fact that this works implies that it is similar in some ways to training a model to do something, right? So if I actually trained a model to, I don't know, predict stock tomorrow, you're not going to look at it and be like, ooh, it's understanding the world. That is not going to be surprising at all. We were able to do this with models for decades. There was no fear of an existential threat. There was no notion of understanding or reasoning in these models because we trained them to do it. And what this shows us is that the same underlying kind of mechanism of training transfers over to large language models in specific instances. And if we use them in specific ways, then maybe what's happening is in each case, we're training that model in that using that same mechanism of the language model itself, which is now no longer interesting because that's not how you create understanding, right? And I will say a little more about this in a second. But before that, we need to understand this idea of instruction tuning, right? So this idea of instruction tuning is really what is between a model that's been trained to predict the next word and a model that is basically able to kind of respond to prompts. So again, this is the kind of tasks that computer scientists look at. So you have this idea of a premise, which is Sally met two actresses, and then you say there's a hypothesis, which is Sally met at least one of them. And then you want to kind of understand if one of them entails the other, right? So if Sally met two actresses, then Sally possibly met one, right? And then that's implicitly implied in that, which means that this is entailment, right? And this is the kind of task that these models are trained on, and this is what the instruction tuning data set looks like. So what we're going to do is we're going to take a task that looks like what's on the left, which is this templatized kind of version of the kind of data sets that you would look at if you're going to throw something into a machine learning system. And then we're going to come up with these natural language kind of words, sentences or descriptions of it. Based on this premise, is this hypothesis true, yes or no, right? And this is what's called instruction tuning. It was again introduced by multiple people, but there's a Flan paper that was introduced by Google, which demonstrated that when you do this, all of a sudden your language models are able to solve a huge number of tasks just by interacting with them. You can't do that with a model that's just been trained on next word prediction, right? You take that model and you ask it something, it's going to just generate gibberish. It's going to generate what might be the next part of such a question on the web, right? Which is not necessarily the answer. Could be a whole host of other questions. It could be anything. But once we do this kind of training, that's when it looks more like, it starts acting like the kind of models that we're aware of. And our second observation is the fact that this now looks suspiciously like the format that's used in context learning. So if you look at how you set something up for in-context learning, and then you look at the actual instruction tuning data sets, and there's typically tens of thousands of these examples, they look suspiciously similar. So which kind of brings us to our next kind of hypothesis, which is that this is probably what is happening, that once you instruction tune a model, when you prompt it, you're probably triggering in-context learning. Now, typically, I would have spent much longer diving into the details of what those experiments look like. But because I think we are more interested in thinking about what this reasoning is and what the implications of that are, I'm going to kind of skim through that relatively quickly, right? So basically what we're trying to say is look, we know that these models can do something interesting, and we want to make sure that we evaluate the functional linguistic abilities, because we're not interested in fluency. All of that is unrelated, right? We don't want that. We're not interested in those tasks. We're going to narrow in on the subset of tasks that require reasoning in people. So we did that. We went through all of the tasks that the original paper found to be emergent. There were 22 of these tasks. And we said, what subset of that would require reasoning in humans? We talked to psychologists to kind of understand this and came up with that list, right? And then we want to know what happens when you instruction tune a model, and how does that influence this notion of emergence, and what does it kind of mean there? So just to kind of quickly give you a feel of the kind of experiments that we ran, here's all of the models that we tested. We tested GPT in a range. Remember, we need to do this across scales. We need to start with a small model, which is what's on top, GPT-2, and then we move up to much larger models. So we start with like a 117 million parameter model, which is GPT-2, and move up to GPT 3.5, which is Text DaVinci O3 at 175 billion parameters. So this is the whole range of it. But that's not enough. What if a completely different family does something completely differently, right? So we look at T5, which is a very different model, and which is a model that's released by Google. We look at Llama, which is released by Meta. We look at Falcon, which is released by an open source group. And we compare the performance of these models right across the board. And here's a list of tasks that we look at. Again, you don't need to kind of think about it in too much detail. But we look at a whole host of 22 tasks, including all of the tasks that were originally considered emergent, and these new tasks that we used as a control, just to make sure that we don't just see that everything is emergent. Okay, So what did we find? Recall that this is what we're trying to do. What do we want to do? So what we want to do is we want to look at base model, which has not been instruction tuned, because I told you there's this additional kind of training that they do. And we want to do it without any examples. So what happens when I go to a model like that? Don't give it any examples, so we're not doing this in context learning. What happens then? What is the model actually capable of? And this is what we're looking for, right? And we actually replicate this to make sure that our results are consistent. So we replicate the original results of the paper. And what do we find? Well, we find that the results are pretty flat, right? This typical notion of emergence is completely lost. It doesn't exist anymore. This idea is gone. If you don't have in context learning, then you don't, basically, these models can't do anything, right? And there are some tasks in which they do slightly better, but then we kind of dive into those and we find that some of them are memory-based and some of them are just formal linguistic, which is, you know, in terms of grammar and so on. So that's not interesting either. Okay, so that's what we say there. Again, so sanity checks, we want to check that this notion of emergence exists. So when we put back examples, I'll come to you in just a second. Right? So when we plug in these examples again, it turns out that we do have this emergence. We do have this jump in performance. So it's not the case that our experimental setup is flawed. It's the case that when you remove ICL, then you really don't have emergence. Okay, and we tried this across Llama. You see the flat lines. We did Falcon. We tried a whole host of different things. It's all flat. Basically, it seems to indicate that without that in-context learning capabilities, these models can't do anything. We also looked at it manually, looked at the actual generated outputs to check that the model, I'm going to again say, understood what the task requirements were and so on and so forth. Okay, so I know I'm going through this a little quickly because I don't want to kind of spend too much time diving into the details of the experiments. I want to just give you a flavor of what that might be.
We did start a little bit late, so don't feel
okay.
time pressure. I think the audience would appreciate some details on the experiments.
Yeah, okay. So there was a question, yes.
So it seems like, you know, especially with experiments.
Yeah.
Classified of instruction tuning or like, you know, IPM, but whereas in your previous slide, you were talking about it being a factor of scale, and I sort of confused about scale specifically. Maybe you have some ground to kind of show that where scale kind of comes into play. Yeah,
no, that's a very good question. So the question was, we're talking about instruction tuning and base models. What is with scale, right? Where is this notion of scale and where does that all fit in? So I should have made this very clear earlier, and that's my mistake. So what we see here is scale. What you see on the x-axis is GPT being scaled from 0.1 billion parameters, it's about 100 million, all the way up to 175 billion parameters. And what we want to see is the phase transition that we saw before, right? We said, look, initially it's not going to do any, it's going to perform at random, it's going to do random performance, but at some point there's going to be that phase transition and it's going to be able to do interesting things. It's going to be able to solve the task, yeah. So that's a good point. So even if we don't instruction tune, so what we showed here was when you don't instruction tune and you provide examples in the input, it will solve it. But when you do not provide those examples, it will not solve it. Okay, so this is where examples, no examples. Yes?
A question on that. For the English proverbs, but it seems like it's getting worse.
Yes, and that's really interesting, right? And it actually, there are some tasks where that happens. And it turns out that when basically, I mean, it's not an exact kind of, so there's the fact that these models were released at different points in time. They were not trained on the same data. Some of them were trained on more data and less data and so on. Now, if we could train a model on all of these, we would control for all of that, but that would cost us hundreds of millions, so we don't. So we take the GPT models, so there is some, you know, difference in terms of what the models are trained on. And you're right, it seems to have that information. Maybe they removed that data set, maybe the addition of other data that's not related meant that this was somehow suppressed. That's not clear, right? But there is something going on there, which is a good point. The claim is that scale helps with one thing and one thing only, which is in-context learning. This idea that when you give it examples, it's going to use those examples to solve a task. And that using that mechanism, you can explain everything that the models can and can't do. Yeah, yeah.
To just give us some details on what the experiments are here. Maybe I missed it, but what's being trained here? Like,
we're not training on anything. So these are base models which were trained on next word prediction, and you provide them with the prompt which is associated with each of the 22 tasks that we looked at. So, and some of the examples that I showed. So in these cases, you do not give them an example first. And in this case, you do give it an example. So you say, here's, I don't know, somebody went camping, they forgot, blah, blah, blah. Here's the options. What is the correct answer? This is where we give a couple of examples, 15 examples followed by the question. Here, no examples followed by the question. When you provide the examples, it solves it. When you don't provide the examples, it doesn't solve it. Okay, so I'm going to take one question, and then I'm going to move forward and then come back to all of it. Go ahead.
It might be obvious, but I think for each of these tasks, all of them have, as part of the benchmark, a 0 shot, few shots.
Yes.
Okay.
Yes, yeah. So that is a very good question. Again, yes. So each of these tasks are part of Big Bench, which is this, beyond imitation game. That was the name of the data set. And it's called beyond imitation game because Turing said imitation game and so on and so forth. And we're saying we need to try if we can do something more than that. It was, again, led by Google. And they came up with all of these tasks, and there's a whole host of them. And this is the subset that they found to be emergent. They said as we increase scale, these tasks suddenly get solved, right? And so we took a set of those, and we added on a couple that they didn't find solvable, just to make sure that we can replicate results. Okay, so again, with examples, without examples. And that's the crux of all of our work, which is with examples you can solve it, without examples you can't. And by you, I mean the model, right? Regardless of the scale, the model can't solve it. Okay, and there's this second notion that I think that I'm gonna talk about, which is basically what happens when you instruction tune the model. And I've said so far that you have these models, which are base models. You just train them on next word prediction. But what really happens when a model you train it on this instruction solving capabilities? So what we're going to do here is we're going to take, and this is again a slightly complex setup, so it's worth spending a second looking at what that means. What we're saying is we're going to take a model that's trained by T5 is a Google model, and it's trained with this instruction tuning capability, so it can actually follow instructions. We're not going to give it any examples, right? Which means that it's not going to be able to use in context learning because we didn't give it examples. We're going to compare what that does with this other model, which is a GPT model. So different company, and we intentionally make sure we do this, separate that out. And this model is not trained on instructions, right? It's just trained on the next word prediction task. And we're going to, in this case, give it examples. So first case, no examples, doesn't know how to follow instructions. Second case, knows how to follow instructions, but doesn't have examples. So now, necessarily, one of them is in context learning, the other one doesn't use in context learning. Now, we're going to compare what it is that they can do, right? That's what is interesting. And you will see straight away, if you just take a quick glance at it, except in those 4 cases that I've highlighted, you will see that both the models either solve the task or don't solve the task, right? Of course, the exact performance is going to be slightly different because the GPT model we test is about 10x larger than the T5 model, which is the Google model, right? Again, that's intentional. We want to vary everything except that task that we test on. We're going to change everything else about it. And yet, they solve pretty much the same tasks, which is quite suspicious, right? And this is what, I mean, if you thought that what I said before this is contentious, this is going to be really interesting, right? So essentially what I'm going to claim now is I'm going to say, look, because these models, so what do we have on the one hand? We know that in context learning exists. We know it's a mechanism that LLMs use. And on the other hand, we can say when they instruction tune it, either they use that same mechanism, which we know exists, or they suddenly wake up and reason. And our claim is, look, it's probably likely that they're using in context learning and that they're not doing anything else, especially because what they can do is pretty much the same thing. Given that what they're doing is pretty much the same thing, they're probably not doing anything interesting. Yeah?
Why is this suspicious?
Because if one model was reasoning and the other model was using in context learning, and I vary everything else about the model, the size, whether it's instruction tuned or not, go so far as to make sure that they're created by different companies. What are the chances that using two completely different underlying mechanisms, I'm going to solve pretty much the same tasks?
Very high if there's a latent variable which could predict.
Which is in context learning.
Well, another latent variable might be difficulty of the task, or requirement for reasoning capabilities, or requirement for some other ability that we just don't know anything about. I mean, there are lots of reasons why these results might be correlated between the pink and the blue here.
Yes.
And you're kind of ignoring all of those other reasons and saying this can be the only reason, but you're claiming that without support.
It's based on the fact that we know that one of them exists. We know that there is a mechanism called ICL. We understand it to some extent, and we know that it can be used to solve tasks. That is our so if we want to think about how we explain something works, we would kind of reach into something that we know exists instead of, you know, making this arbitrary kind of assumption that there's some kind of underlying reasoning.
How would you directly respond to my comment that there could be a latent variable which is resulting in these results, the pink and the blue results being correlated? I mean, they're not even perfectly correlated because, as you've highlighted, some of them they differ. So how do you directly respond to my claim that there is a latent variable responsible for these results, got nothing to do with ICL?
Well, my response to that would be, if that is reasoning, then the onus is on you to demonstrate that.
I haven't said anything about reasoning. I'm just saying there could be a confounding factor. I mean, you're kind of ignoring the fact that there's a confounding factor. There could be a confounding factor, which is kind of at the heart of scientific research, to figure out what the confounding factors are and rule them out. You're just saying, well, let's just don't worry about it.
That's not quite what I'm saying. Like, I think what I'm saying is more nuanced than that. What I'm saying is that, yes, there are confounding factors. We're going to control for as many of them as we possibly can. Given this, we are now going to run very controlled experiments to see what models can and cannot do. We're going to reach into the theory that we have access to in terms of what they can do. And we're going to use that and use the fact that in general in scientific research, we want to use the simplest possible explanation and not reach into something like, oh, the model suddenly woke up, as an explanation for reasoning. And using this, we're going to say, look, if before we jump to the conclusion that there is an existential threat posed by these models, which leads to hundreds of millions of dollars being poured into this, as opposed to actual issues such as fake news, such as phishing emails, which are generated by LLMs, which now are in perfect English. If we're going to take money away from these real issues and pour it in somewhere else, then we shouldn't believe that this is a done deal. There are questions to be asked, and that is what we're doing. We're saying this is
really about any of that stuff. I mean, you're invoking Occam's razor. You're saying you should stick the simplest explanation of the results.
Yeah.
The simplest explanation of these results that you're presenting here is that some of these tasks are really hard and some of them are really easy for neural networks, for example. Now, that's like a really simple explanation of these results. It obeys Occam's razor. I just don't understand why.
So what would that mean? So then, based on Occam's razor, what would that mean? So what would your claim be?
There is some that some of these tasks are just really hard for neural networks.
And so what would that say about reasoning?
Well, I don't need to say anything about it. I just need to say there could be some latent variable, let's call it hardness,
okay,
which means that neural networks of different characters, trained by different companies, as you've said, are going to find some tasks hard and some of them easy.
Yes.
I mean, I will. Top of my head because that's like.
But I will now. I'll explain how this explains that. Basically, that is necessarily true if you have a model that you train and it can solve certain tasks and cannot solve certain tasks. It is necessarily the case that some tasks are harder and some tasks are not. Otherwise, if I train a model on any task, it should be able to solve it. The fact that there are some tasks that are not able to, that you can't solve, necessarily means that there is a variation in hardness. And what we're saying is that that is captured by in-context capacity. The expressive power of in-context learning will explain that, and not some arbitrary failure in reasoning. So that is the crux of it. So what does that translate to? It translates to this, and this is, again, not explicit. This is pretty much a way of thinking about it, right? So what does it mean? It means that if you go to a language model and you say, oh, you know, this thing says brings a smile to my face, what is that? Is that positive or negative? Now, the way to think about this, and again, it's important that this is not what a language model is doing, but the way to think about it is it's going to convert that to exemplars and then use that to somehow solve this task. And I'm going to tell you what that means in terms of what the language model can do. I'm going to skip these couple of slides, which were basically, again, controlled experiments to make sure that, you know, we actually deal with those latent variables that we were talking about. And notice how our theory explains things like the need for prompt engineering. It means that if you set up a prompt, I'll come to you, I'm almost done, and then I will definitely come to you, I promise, right? And the same, I think there was another question there, right? So what does it mean? It means that if you set up a prompt in enough detail that the model can use the information in that prompt to, I'm going to again say, set up those exemplars, basically have all of the necessary information to solve it, then it's going to be able to solve the task. But if you assume that the model is going to reason for you, and complex reasoning, where again, the task complexity is higher than some X, then it's going to just fail. And that is why we need this prompt engineering. And that is how we explain the need for prompt engineering, which a language model that's understanding is not going to, that's not an explanation for it. Like if a model understands, again, I'll come to you in a second as soon as I'm done, right? Sorry, right? As soon as a language model, if a model is indeed understanding, then it doesn't need that. What about hallucinations? Well, if you don't set it up properly, then the model is going to reach into the most statistically likely output and chuck that out. And what does that mean? Well, it's going to hallucinate, right? And that is really how we explain how these language models work in terms of the underlying mechanism. Okay, so this is a summary of conclusions, but I think this implications is what is really interesting. It's the fact that these models have been either called statistically most likely output, the stochastic parrots. They just chuck out something that's most likely, or people think that they're reasoning. And we're saying no, the answer is somewhere in between. And there are other things that we need to think about, such as in context learning. Maybe there's yet another latent variable, like you mentioned, in which case we must explore that and we must find that. But to say that, oh, either they're just stochastic parrots or they're going to wake up is not really science, right? These are the two extremes that we've been looking at. We need to find something in between. So what does that mean, finally, to how you might use this model? Well, I'll come up with like just an example, but that could be your favorite task that you're asked to do. If you just ask a model, how can you do this? That's not, I mean, in this case, it'll answer it because it's a fairly obvious question, but that's not the best way to do it. The better way to do it is you take content associated with that, and then you kind of add that in context, and this is where RAG comes in. You add that relevant content, and then you ask a question based on that. But the really best way to do it is come up with content, question associated with it, the required answer. Come up with a couple of examples that look like that. And then once you fit that in, then you come up with your actual question. And now you're really triggering in-context learning. And if you can do that effectively, even in instruction-tuned models, then the chances of you getting the correct answer and the model hallucinating less, getting the correct answer higher. So if you're going to use this, I mean, if you take nothing away from this, this is the slide that matters, right? If you're going to use it, give them a couple of examples, and that's going to be interesting. Okay, so I'm very close to being out of time, but I did promise 3 people that there was a question here. I think you had a question. Yes.
Yeah. 10 minutes.
Oh, thank you. Okay, we have 10 minutes. Okay. Yes, of course.
Is there some kind of trade-off between this ability of ICL and scale? In other words, if a model with 700 parameters can do basically the same job of a model with 7 billion because you actually formulate the prompt properly.
Yeah.
So at what point does the arm race needs to go? Like, you know, because people are building bigger and bigger sledgehammer to crack nuts.
Yeah.
But maybe we don't really need to go there and spend a lot of money on data centers, GPUs, etc., etc.
Yeah.
If ICL is the cornerstone that can make a 700 million parameters perform like 7 billion?
That's a good question, and I think it might be okay. So let me repeat the question. So the question was, if ICL, if we can we somehow assign some complexity of, what is required to how powerful ICL is, and does it kind of plateau at some point? Is that? I don't think it does, but I think where it does plateau is when we run out of training data, and that's kind of where we are in terms of the scale of these models. So what's really interesting is it's not the entire kind of picture isn't so simple, because there's these fee models that Microsoft has released, which are much smaller. They're 2 billion parameter models that are on edge devices, because obviously you don't always want to kind of send prompts out. And they do really, really well, better than some of the much bigger billion parameter models. And the question is why? Well, it turns out data quality is the other parameter that's relevant, the quality of the pre-training data, right? So if you're going to train your model on very precise data, it's going to reach that capability faster than if you trained it on Reddit, right? That's now it's going to take ages to get to something interesting. So I think there's a lot of things there, and people are, I mean, it's a very active area of research, because of course we all say billions if we can do that. There was I think you had a question, yes.
We demonstrated that in context learning is not an emergent property.
Aha, that's a very good question. Yes, indeed. So the question was, how do we know that emergent ability, in context learning itself is not emergent, right? There's one very important element about this idea, this notion of emergence. It's the fact that it is not predictable. In context learning is. You can see it at smaller scale. It does less interesting things. But as the model gets bigger, it can now do more interesting things. It can solve more complex tasks. But it is definitely something that we can observe even in GPT-2 models, which are under 1 billion parameters. And so, because remember, why are we worried about emergence? Because if we can't predict it, it might plan and it might wake up. That's scary, right? So that is why, and otherwise it's just semantics. But there's this important distinction in terms of what it can and can't do. So you had a question, yeah.
My question is, I'm not talking about reasoning or not reasoning, but let's say, let's think about it as thoughtless thinking or reasoning, Chinese room type.
Yeah.
So the question is it really scary? So is it really dangerous?
Yeah.
What the danger is, actually?
That's a really good question. And I think, so yeah, I think that is really the crux of it. So let's see what it means to say that ICL is what is being used, right? So what does that mean? It means that when I pick up a model and I prompt it with something, what it's going to do is it's going to use the prompt to isolate that subset of the pre-training data, which is basically web data, that is relevant to my prompt. It's going to find patterns in that pre-training data, which is in the web, and then it's going to answer my question, which directly explains your question. What about these adversarial scenarios? Why do they fail? Because they're not in the pre-training data. The minute I move away from that, they fail. So to me, there's something else that we can do, which is why we're sample efficient. I don't need to read all of the web to be able to even talk for an hour, right? And that, I think, is the distinction. And what the model is doing is it is generalizing from all of the web, which is really, really powerful, because all of the web is a lot. It's a huge amount of data. And if I can generalize from that and think, going from linear regression to whatever, right? And you can generalize from all of the web, that is significant. But it's still not quite novel reasoning, right? There's a distinction in my head which seems quite clear. But what else it translates to is the fact that if we have medical data that we throw into the model, it's going to fail because there isn't that much of it in the pre-training corpus. Like there's scenarios where you say things like, I have 3 sisters and they have 2 brothers, how many brothers I have, or something like that. Some of the GPT 3.5 models fail because really nobody talks that way on the web. So that, I think, is the real consequence of this idea that it makes use of pre-training data to extract patterns, right? Yeah.
In the case of like the newer models from OpenAI, like O1,
yeah,
where they've been trained to reason, like from the beginning, right? During the pre-training stage, they've been trained to reason, then filter out what the answer is, and then give you the final answer. Like I mean, at what point do you consider that as just next token prediction versus is it actually thinking, or like it's just a really hard definition to make like at that point?
Yeah, that's a good question, right? So the question was, what about all these O1 models, right? What about GPT-4? We also test on GPT 3.5, but not 4. So maybe they're doing something. And I think there's a distinction. So first of all, I'm not saying that it's either next token prediction or reasoning. I'm saying that there is an in-between, which is ICL. It's a combination of ICL and next token prediction. When you don't trigger in-context learning, it's going to fall back on next token prediction. And I think that is the crux of why GPT 401 or whatever still is the same kind of machine. Because when you see it fail, when you see it hallucinate, and here's one of the things that it does hallucinate on. If you go to a GPT, I mean, probably they changed it and updated it now. But if you ask it, what is 0.8888, recurring equal to 1, 401 used to say yes until 4 days ago, a week ago when I saw it, right? Why is that? Because most of the stuff on the web talks about 0.9999 recurring being equal to 1. So in my head, it's not about the fact that they can fail or they sometimes fail or sometimes don't, because we sometimes fail and we don't. It's the fact that when they fail, they will output something that is statistically likely. To me, that demonstrates that this is what they're doing. If it went ahead and said something completely different, then I'll be like, oh, something else is happening. But it doesn't do that. When it makes a mistake, the mistake is always a statistically likely output. And that, I think, is why these models are not. There was a question here. Yes?
The emergence, the scales are very sort of logarithmic on the graph because there's a big gap between, because the larger models. Is it that if the scaling doesn't continue to be logarithmic, that the emergence isn't quite so
dramatic?
marked?
Yeah, no, that's a really good question. So the question was, it's incredible that you observed that the x-axis is actually logarithmic, right? And you'll see the scale is actually linear. So what does that mean? And there's actually a paper from Stanford that says that this isn't all unpredictable because, at some point, what we plotted in log scale, if we plotted it linearly, which would be really annoying because it would be really long, but then you'd see that it is indeed predictable. But the point is, and I think this is a precursor to the actual answer, is the fact that they don't perform like, sort of kind of okay and suddenly start performing well. They perform at random baseline, like they perform just completely random and then suddenly take off. And so, yes, that scale could be quite dramatic or it could be quite uninteresting. But the fact that it does something beyond this random is already, I think quite interesting. Okay. Do we have time for another? One more question. So I'll ask somebody who hasn't asked before. Yes.
So if I understand correctly, we've got scale of data, and then you've also got instruction tuning or in-context learning. But you can't need them both to get the amazing ChatGPT experience that we get.
Yeah.
We're running out of data, I think, as you said, because we're running out of the internet.
Yeah.
What happens if we scale instruction tuning?
And I think that is, like you said, that is the heart of what O1 probably has done. We don't know because we have no information on what they've done. But yeah, that's a really good question. The question was, there's pre-training data, there's instruction training data. We kind of run out of pre-training. What if we train on a lot more? And they have trained on a lot more. They've trained on pretty much any task that anyone could have thought of. And all of the research that we've done in showing that GPT 3.5 failed on something, they took that data and then they trained this larger model on it, right? So their idea is that, they're like, there's never going to be out of domain. That's not a thing you will ever find. So if we make everything in domain, then the model's going to be able to solve it, right? And also there's quality of data, which is the third bit that will contribute to ICL performance. But thank you very much. It was absolutely fantastic. That's me. So if you want to get in touch, please do.
Thank you so much, Harish. I invited you along because I thought that we'd get some good debate and some good questioning going on. Yeah. So thanks so much for the discussion. And let's go.
I'm here, so if anyone wants to chat, then
fantastic. Yeah. And thanks again to Mango. Thanks to James. Beer is served now, is it? We hope.
Well, the door can tell us.
Oh, there's some pizza. Let's go. Thanks so much.
Yeah, absolutely.
Yeah.
Thanks for having me.
Do you want a bit?
Yes, I'll definitely join. I think I need one.